Hi, and welcome to this session entitled Explore Fault Isolation Boundaries on AWS. My name is Mark Jones and I'm an AWS Solution Architect based in Melbourne, Australia. I find the subject of fault isolation a super interesting and incredibly important one. AWS has been building with fault isolation boundaries in mind since the very beginning, and in the many years I've been working with customers to uplift their resilience posture on AWS. I honestly believe it's one of the most important and sadly misunderstood concepts. So in today's talk, we'll explore the concepts. We'll learn about the common fault isolation boundaries in AWS, look at how AWS uses them in their own service design, and finally wrap up with some recommendations you can implement to increase the fault tolerance of your own services. So I said before that I think this is an incredibly important topic. But why? I'm sure you'd agree that we're currently witnessing nothing short of extraordinary times in the software industry. The appetite for innovation, both from end users and our internal stakeholders, has never been bigger. And luckily, the tools to enable innovation, never better. Adding to this, the accessibility of cloud and faster networking has led to the development of highly distributed and sophisticated system architectures. Complexity is on the rise, with more and more dependencies being incorporated into services all the time. The expectation is that we're all delivering smaller changes faster, with the rate of change always accelerating. And let's face it, with every change comes an element of risk. And all this in a time where customers' tolerance for failure is decreasing. It's no longer acceptable to be down, even in the face of failure. And whilst I'm sure this resonates with you as a customer, it's also the world that we at Amazon Web Services operate in. We're delivering faster than ever, and internal and customer expectations have never been higher. So we've learned a thing or two over the years about service resilience in the face of failure. And as builders, boy do we have loads of potential failure types to think about, ranging from the more frequent issues like bad deployments, and quietly this is clearly the number one risk I see with customers, right through the highly unlikely scenarios on the right. Of course, these are very unlikely to occur, but for some customers, they still need to consider and plan for them. So assuming that failures will occur at some point, what can we do to increase the likelihood of remaining available? Well, it's truly a shared responsibility between AWS and you as the customer. AWS takes responsibility for resilience of the cloud, ensuring that the infrastructure backbone composed of hardware, software, networking, and facilities, which runs all of our services, is highly resilient. We're going to talk a lot more about this shortly. And with AWS taking responsibility for resilience of the cloud, customers therefore become responsible for resilience in the cloud. This is super important because in the context of fault isolation boundaries, AWS takes responsibility for ensuring that things operate and fail in predictable ways. But you as the customer need to understand this and to design your systems with this in mind. But before we do go deeper, let's take a step back and better understand what a fault isolation boundary actually is. A fault isolation boundary limits the effect of a failure within a workload to a limited number of components. So you may ask, why is this important? Well, components outside of the boundary remain unaffected, allowing you to avoid correlated failures and remain available and serving requests even when issues are encountered. It sounds like a pretty good outcome, right? When you think about it though, this is not a new thing. We've been wrapping code blocks in try-catch statements for years. It's just the scale it's applied to that's a little different. So let's make it real and explore some specific fault isolation boundaries that exist within AWS. I'm sure that everyone has seen this diagram or similar, describing how AWS builds and deploys global infrastructure. But let's look at it briefly in the context of fault isolation boundaries. With the launch of the new Melbourne region, the AWS cloud now spans 31 geographic regions around the world. Regions are separated to contain service failures, meaning that when service impairments do occur, other regions are typically unaffected for their normal operations. Each AWS region consists of 3 or more independent and physically separate availability zones, or AZs, within a geographic area. The AZs in an AWS region are interconnected with high bandwidth, low latency networking over fully redundant, dedicated metro fiber, providing high throughput, low latency networking. Each availability zone in a region is separated by a meaningful distance from the others to prevent correlated failures, but close enough to still support synchronous replication. They're designed to avoid being simultaneously impacted by a shared fate scenario, like power or water disruption, fiber isolation, earthquakes, fires, tornadoes, or floods. Common points of failure like generators and cooling equipment are not shared across availability zones, and they're designed to be supplied by independent power substations as well. Importantly, like regions, availability zones are designed to minimise the blast radius of failures, meaning that issues that occur at the availability zone level in one AZ typically do not impact the other availability zones. Finally, each AZ is made up of one or more discrete data centres with independent and redundant power, infrastructure, networking and connectivity. In addition to the AWS regions and AZs, AWS also operates a globally distributed point of presence or POP network. The global edge network currently consists of more than 410 POPs, including over 400 edge locations and 13 regional mid-tier caches in over 90 cities across 48 countries. These POPs host Amazon CloudFront, Route 53, a public DNS resolution service, as well as Global Accelerator, an edge networking optimization service. Each POP is isolated from the others, which means an event affecting a single POP, or even an entire metropolitan area for that matter, does not impact the rest of the global network. So we briefly talked about regions, availability zones, data centers, points of presence or POPs, but we also have the concept of partitions. AWS partitions are a group of distinct regions where every region is in exactly one partition, and most partitions have multiple regions. The one that almost everyone is familiar with is the AWS commercial partition. That's the one the vast majority of the public operates in, and it contains AWS regions like Sydney, Singapore, and the recently launched Melbourne region. Alongside the commercial AWS partition, there are also other partitions for China and GovCloud in the US. Partitions create a boundary around AWS accounts, data, and resources, and as a result, each partition has its own instance of essential services like IAM. Even when AWS services provide cross-region functionality, such as Amazon S3 cross-region replication, these types of capabilities are only supported between regions in the same partition, and you can't use IAM credentials from one partition to interact with resources in a different partition. So we've just covered some of the better-known fault isolation boundaries that make up AWS's global infrastructure. But now let's explore a less widely understood concept, that of AWS service control planes and data planes. The terms control plane and data plane originated in the world of networking, specifically routers. What do routers do? Packets in, packets out all day. That's the data plane. But the rules have to come from somewhere. They have to be created and distributed, and that's the control plane. Applying the same pattern to our own service design, AWS engineering teams strive for the same separation of concern, effectively carving up our services into control planes and data planes. The control plane for AWS services typically include operations that create, delete, list, and describe resources. These operations are often complex with more dependencies, and as a result, more that can go wrong. Whilst the data plane is the day-to-day operation of resources, simple and dependable. As a customer, this is important to understand because control plane and data plane operations have very different design priorities and should be thought about very differently when being considered as a dependency. Here are some examples of the separation between control plane and data plane across a couple of different AWS services. I'd suggest the most clear-cut example to focus on in the list here is DynamoDB. The control plane operations are responsible for creating or updating a table, whereas the highly available data plane operations are leveraged for retrieving or persisting data in the table itself. To further explain, let's look at a more concrete example with EC2. Here we have two EC2 instances communicating back and forth. This is the data plane of EC2. If I was to call run instances to get a new EC2 instance, I make the API call, and in a few seconds, a new instance starts. But in that time, lots of complex work has to go on behind the scenes, finding capacity and availability zone, creating and attaching EBS volumes, creating short-lived IAM credentials, allocating network addresses, updating internal DNS, distributed networking rules, etc. That's all done by the control plane. And now finally, we have 3 EC2 instances, all sending data back and forth. But why is this important, and how will it help to keep your services available? The answer is static stability. But what is static stability? Static stability means a system can operate in a static state and continue to operate as normal without the need to make changes during a failure or unavailability of a dependency. But I really like the more simple definition. Static stability means having dependencies but not sharing their fate. And this concept equally applies to both AWS service dependencies and any other type of system dependency. So why is this important in a session about fault isolation boundaries? Well, service control planes and data planes are themselves a type of fault isolation boundary, helping to maximize service availability for customers. And when failures do occur, because AWS service data plane operations strive for static stability, in most cases, an impaired control plane will not have a negative impact on the data plane if a workload is truly statically stable. So returning back to the previous example on EC2, take the EC2 data plane, instances running on physical servers. The physical servers have some software on them, storing state for things like the VPC, mappings to reach other instances, etc. In the face of a control plane impairment, the physical hosts continue to operate and could even reboot and still carry on running your instances for a period of time. Of course, in this same example, control plane operations like EC2 run instances would fail to execute, but the day-to-day operations of the resource deployed would continue to work and serve customer requests. So as I mentioned, we're first talking about control planes and data planes. Each typically have very different design objectives. For more and more of our services, they're making these design objectives publicly available for customers. And I've included a QR code for a list of these on the slide. Separate from design objectives, it's also worth noting that our service level agreements are also structured around the idea of control planes and data planes. Most published SLAs for services provide commitments for the day-to-day operation of the service, which is the data plane, but not for control plane operations. For customers, this is critically important to understand and reflects our recommendation around avoiding control plane operations as runtime dependencies. After all, remember that AWS service control plane and data planes strive for static stability, protecting resources that are already running, but this will not protect workloads that rely on infrastructure being provisioned just in time. To mitigate this risk, think seriously about pre-provisioning where possible, or leveraging data plane operations like Route 53 health checks to change behavior where required. But we'll talk more about this shortly. So now let's take a closer look at the types of AWS services available today and talk more about how they make use of the concepts we've covered in the session thus far. At the highest level, you can categorize AWS services into 3 types: zonal services, regional services, and global. Zonal services like Amazon EC2 and RDS operate independently in each availability zone within a region, and more importantly, fail independently in each availability zone as well. This means services in one AZ minimize dependencies on services in another AZ wherever possible. Zonal services allow you to deploy multi-AZ architectures to be able to withstand the failure of a single availability zone. They have a zonal data plane and a regional control plane. Regional services are those that AWS has built on top of multiple AZs, so that customers don't have to figure out how to make the best use of zonal services. We logically group together the service deployed across multiple AZs to present a single regional endpoint to customers. Amazon SQS and Amazon DynamoDB are great examples of regional services. They use the independence and redundancy of availability zones to minimize infrastructure failure as a category of availability and durability risk. Importantly, these have been built to be statically stable to AZ failures, However, in some cases, their ability to withstand AZ impairments can be limited by the choices you make, like how many subnets or availability zones are used to deploy the service. Regional services have a regional control plane and data plane. Finally, in addition to zonal and regional services, there are several other services whose resources aren't constrained to a single region. Because their resources are not localized in this way, they're commonly referred to as global. However, this term can be misleading. What this really means is that these services still follow the conventional AWS design pattern of separating the control plane and data plane, but the service has a centralized control plane in a single region and a distributed data plane that exists independently in either every AWS region or even POPs. If we think back to the slide on partitions, most global services exist in each partition, like IAM and organizations. In the AWS partition, these two services have the control planes in US East 1 and also have isolated data planes in every region in the partition. The same is true for the other partitions as well. The other global AWS services are the ones who operate their data plane in the global edge network. These services include Route 53, CloudFront, and Global Accelerator. These two have a control plane that operate in a single region, but either US East 1 or US West 2. When building applications on AWS, you need to be aware of the different constructs, global, regional, and zonal, when choosing AWS services. You need to think about the impact choosing a particular service type has on your part of the resilient shared responsibility model and on your application. One small caveat. You know when I said S3 is a regional service before? There's a slight twist to this. Because S3 bucket names need to be unique across the globe, the S3 bucket map service is global and located in US East 1. If this is not available, customers won't be able to create new buckets. This also demonstrates why static stability is so important. Minimizing control plane dependencies in your critical path is super important for resilience. So here's a deeper view on how we provide availability zone independence for zonal and regional services. We have data planes and control planes in each availability zone that are isolated from one another. Then we provide a regional control plane that handles things that are not zone specific, things like managing security groups in the case of EC2. The regional control plane is also responsible for aggregating API requests, like, for example, EC2 describe instances, where each of individual availability zone control plane needs to be queried before the right results can be returned. But what happens when there is a service disruption impacting the EC2 control plane in a specific availability zone? Well, describe instances will continue working for other availability zones. You just pass a filter, excluding instances in the affected area. The great thing is that EC2 has documented this behavior, and I'd suggest it's well worth understanding if you have EC2 as a dependency. And let's face it, who doesn't? Whilst not all services are designed exactly like this, most follow a fairly similar pattern. When it comes to global services, there are three main categories. Services that are unique by partition, I'll refer to these as partitional. Services that operate in the edge point of presence network. And a third category that are not entire services, but specific functionality or operations in a service that have a global scope. Each one of these services in the first two columns have a control plane that's hosted in a single region. And these can present single points of failure in your workloads, especially in your recovery paths. The third group of operations also have a global dependency on a single region, and these can also represent single points of failure in your workloads. Let's take a closer look at one of those partitional services now, Identity and Access Management, or IAM, to understand how global services are architected a little more deeply. Here we can see the data plane of IAM. It exists independently in every AWS region. Each AWS service in the region interacts directly with the IAM data plane to authenticate and authorize the requests they receive. Then we have the control plane. It's what you use to manage IAM resources like identities and policies. So when you call create role, that flows through the control plane. The control plane is also responsible for propagating those changes everywhere they need to go. In this case, each and every region across the partition. In an IAM control plane impairment, the data plane operations, so authentication and authorization, will continue to work in each region, but updates may not be received from the control plane. It's eventually consistent after all. Importantly, because global services have a single control plane, we have to be very careful about the runtime dependencies we take on them, and to keep the pattern of static stability in mind at all times. This is never more critically important than during recovery operations. One of the primary best practices for global services is to avoid relying on the control plane actions in your recovery path. This is because control planes are statistically more likely to fail, and for global services, they only exist in a single region. Relying on their highly available data planes for recovery is a more reliable pattern. And this is a form of static stability. You're effectively making your recovery path statically stable to a failure of a global service control plane. In fact, when you think about it, you can apply this guidance to any service, including zonal and regional services. Since we know a dependency on a data plane is better than a control plane, your recovery approach will be far more reliable applying the same guidance to any service dependency you take. Here are a few examples of global services and what will work and what may not work in the face of a service control plane impairment. These aren't all of the global services I showed you earlier, but some of the most commonly used ones, especially when it comes to recovery. A common anti-pattern I see all the time with AWS customers is that as part of a recovery plan, there's a step to update DNS records or to grant additional access to resources using IAM. Both are considered control plane operations and therefore statistically less likely to be available when you need them the most. So in closing out this session, I'd like to leave you with a few recommendations that will make your own architecture more tolerant to failures. Like AWS, design, deploy, and operate your services with the aim of containing the blast radius of failures. Think about gradually introducing changes, align deployment stages with fault isolation boundaries to minimize the impact of any potential issues that might arise. Remember, configuration and deployment issues are almost always the #1 cause of failure within an architecture, so it's well worth developing a strategy to mitigate the risks. For fault isolation boundaries within your systems, implement and align observability so that you can quickly understand the scope of failures and act accordingly. I find CloudWatch great for this, where you can leverage metric dimensions and set up dashboards and alarms for common AWS fault isolation boundaries, allowing you to quickly understand where and when your failures are occurring. When designing services, think very seriously about the dependencies you're taking on, both at run and recovery time. Anytime a request crosses a fault isolation boundary, it introduces risk to your workload, so avoid it wherever possible and implement strategies to achieve static stability where it can't be avoided. Finally, understand the different AWS services you're leveraging. They're built to operate and fail in very predictable ways, so take the time to understand the modes of failure for each service you're using and how and when to use both control plane and data plane operations in your workloads. Thank you for your time. I hope you've learned something new today and taken away a couple of new ideas that can help to uplift the resilience of your own architecture. If you enjoyed this session and are interested in learning more about the AWS platform, check out Skill Builder and explore over 600 free digital courses, hands-on labs, and role-based games. I was looking the other day through the site, and there's a really good free course on Skill Builder for AWS Resilience Hub that I personally think is well worth checking out. Anyway, thanks again for your time. I really hope you enjoyed the session. Please don't forget to complete the session survey. Your feedback is important and means a lot. Thank you.